Hi guys, so today we're going to talk about this question as part of this general overall question. And basically we're going to talk about the subject, how do we apply the empirical rule to other distributions and why should we care? And so the first thing to really understand about all this is you first have to go really basic. Do you understand what the empirical rule is? So if I go look it up, I receive this graph, and there are a couple parts of this. As you follow my cursor around, the empirical rule is always shaped like a bell. It also, like a bell, is called a normal distribution, and 68% of your data lies within one standard deviation from this 0 point, which is your mean. 95% of your data lies between 2 standard deviations away from the mean. 99 lies between 3 standard deviations away from the mean. You can also rephrase how you think about this, and instead of actual data points, you can think of it as the probability of occurrences. So if you are predicting a population mean, one of the things that you are actually doing is you're saying, I have this random population mean right here, and I'm going to take tons and tons and tons and tons and tons of samples to try to predict that population mean. And theoretically, if your population mean is right here, and you're taking tons and tons and tons of samples to predict that population mean, the most frequent occurrences of your population mean will be in the middle there. Theoretically, because if your sample is a true predictor of the actual population mean, when you're taking samples of it, your sample means, in terms of their frequency, are going to cluster around that population mean. And you will theoretically have a normal curve like this. That's another way to think about the empirical rule. You can't really apply the empirical rule to binomial distribution until you really understand it. And another way to think about it is really, instead of data, you can have frequency or probability of occurrences of particular outcomes. Because if you're thinking about it in this light, you're taking multiple samples and you can plot the frequency of occurrences of different means. And theoretically, you should have more frequencies of occurrences of different means when they're closer to your population than when they're farther away. It sort of forms some of the basics of inferential statistics, which is sort of a key portion of that. This is called the sampling distribution of the mean. And it's just really showcasing that in this case, you can apply the empirical rule because in general, you can apply the empirical rule even with probabilities or with frequencies. In each of these points, it's a probability of occurrence and a frequency of occurrence of that particular sample mean when it's trying to predict the population mean. And you have 68% of those probabilities of those occurrences in the middle, 95 2 standard deviations away, and 99 3 standard deviations away. What I'm trying to do with this short explanation of empirical rule is really get you guys thinking beyond just data. Empirical rule doesn't have to be sort of centered and closed in around data. Empirical rule is also functioning around frequencies and probabilities of occurrence. And this is sort of the proof of how we sort of know that. We go to something that we're a little bit more sure about, that we're taking sampling means, trying to predict the population mean, and we're going to have more of those occur when we get closer to the population mean versus when we get farther away from the population mean. And the probability of occurrence of those means is going to be higher. And as a result, we are approximating a normal distribution. And if we're doing that, we are approximating an empirical rule as well. Or we're getting pretty close to at least understanding a little bit more of that. I'm drawing this because I want to really showcase that you have more occurrences of the population mean in your samples as you get closer to it. And so you have more data, in a way, in your samples as you get closer to it. I really want to make this connection. Now, the second thing that you have to understand, if you really want to apply the empirical rule to maybe a distribution you haven't applied to yet, is you really have to understand the other distribution and how it looks and what it's really all about. So let's do that with this. This is a binomial distribution. You know that because email can be either spam or it can be not spam. You can draw this, you can visualize this with an x-axis, 0 emails and 500 emails, by understanding that all along this x-axis are different occurrences of a different amount of emails. So this is 2 emails, this is 3 emails, this is like 479, and so forth. You could also do a calculation called expected value to get what we would call the mean. And that's just the sum of all the outcomes times the probabilities, which is really 500 times 5.546%. Let me just rewrite that so it's a little bit clearer to understand. It's 500 times 0.546 or 273. So if we're really going to visualize a binomial distribution well, we're putting that expected value, 273, in the middle there. That is the expected amount of emails, given 500 emails, that we would expect is actually spam. All right, next step. We got to figure out what this y-axis actually means. And so what I really want to draw your attention to is the Excel functions on this, because I don't really want to do math right now. So the Excel function is binom dist. And let's do it for 273, shall we? So we're going to go equals binom dist. Our number of successes. We expect 273 out of 500 trials are going to have spam. Successes, what we're defining as success in this problem, is spam. And so how we do this is we type the 273 emails we expect is going to be spam. We have 500 potential emails to draw from. The probability of spam is that, and it is at 273. If we do cumulative, that means that we're doing 273 or less than that. The probability of spam, 273 or less than that. Let's see what we get. You get about 50%. What I want you to see is that is why this is our middle value. That is why this is our mean. That is why this is a smack dab in the middle of the other ones. The probability of occurrence of anything less than 273 being spam is 50%. Now let's take this one step further. We can calculate using the Excel function this, binomdist, exactly the probability of one email being spam. Binomdist, the number of successes, we just want to know what is the probability a singular email is going to be spam. 1. Trials out of 500, probability 0.546. Cumulative, no, we're doing a single email. That is some ridiculously negative number. And I'm going to format it out so that you can see what it is. If I can remember how to do it, sometimes I forget. But let's go to number. And we're going to go to a crazy amount of decimal places. So it says 169. We're going to go to 99999999999. It doesn't even read it. We get a 0.00. This is a ridiculously low number. What that's saying is if we go to our chart and we were to draw the probability of occurrence of 1 or the particular outcome of 1, it'd be ridiculously low. I'm not even sure that you would even see it. And I'm drawing this conclusion to try to illustrate that when we were doing the sampling distribution of the mean, where we were saying that you can actually apply probability and frequencies to a normal distribution, we were saying that in essence, when we have sample means that are out here, this represents a certain frequency of occurrence, and it represents a probability of occurring, especially since all our numbers are close to here, so this is going to be a low probability of occurring. It's a low probability that you will have sample means at that point, whether that point is like 2, 5, 7. A sample mean out there has a low probability of occurrence because this is a predicted population. And what we know is that if our sample mean is a good predictor of the population mean, then most of the sample means we would get by taking 5 million samples are going to cluster around the population mean. So right here, this point represents both the frequency of occurrence and the probability that that outcome, that X value, is actually going to occur. So let's draw that corollary again to binomdist so that we can actually see what we're talking about. This thing that we did for 1 represents the probability that 1 email exactly out of 500 is going to be spam. And we can do that. We can keep going. We can assess the probability that 2 emails out of 100 is going to be spam. We can assess the probability that 3 emails out of 100 is going to be spam. And we might actually be able to do that and draw whatever that distribution actually looks like by assessing all 500 different probabilities. So that, like, we assess the probability that exactly 273 emails are going to be spam. So let's do that. Equals binomdist, number of successes, 273 emails exactly are going to be spam. Trials, 500. Probability of occurrence of spam for that, and then exactly 273. And it's interesting because what you see is the probability that exactly that is 0.0358. It's not our 50%. So what does this mean? This means that the probability of occurrence of this 273 number is and let's go back to make sure 0.0358. 0.0358, which also means that the probability of occurrence of 273 emails or less, and I'm going to actually highlight it to make it a little bit more clearer. So the probability of occurrence of 273 emails or less is going to be that 51% we came up with earlier, 0.52. 0.52 or 52% for our expected value, which is a value we would expect if we're predicting our expected out of 500 emails when 54.6% are spam. Our expected amount of spam emails is 52%. And what I want to show you is there's a difference between binom dist when you end with 1 versus binom dist when you end with 0. When you end with 0, it gives you this y. When you end with 1, it gives you the area to the left or the area to the right. All right, now the final thing that we need to talk about. How can we actually know whether or not we have the empirical rule apply? I think I've done a really good job of sort of showcasing that you can make a distribution out of the binom dist, and that your distribution could, in fact, look like the empirical rule if your numbers work. But let's actually work this out. So I'm going to erase some things. And so remember, in the empirical rule, you have to have some things that hold true. One thing that has to hold true is that one standard deviation of the mean has 66%. Oh, 68% if I'm getting it right. 2 standard deviations of the mean have to have 95%, and 3 standard deviations have to have 99%. And you can actually, using the Excel formulas for binom dist, calculate what that middle value is. So let's just do one standard deviation, shall we? Our 68% of our value is in the middle of that. So, equals binom dist. And we want to find this number first, or this number first. So whatever that is, then we want to find this number second, whatever that is. And we want to know what is 68% in the middle. What we can do is we can take the second part of this equation where it says, what is the standard deviation of emails? Define this one and this one. It's not ST-dev. When you're finding standard deviation in binomial distribution, you have a particularly unique formula. So let's look it up. So, standard deviation in binomials. So here's the formula up here. And I'm just going to take a look at what this website brings. So standard deviation is the square root of n times p times 1 minus p. So what is n? And let's see how this website defines n. N, come on, scroll up. N is the number of trials. P is the probability of success on any individual trial. So the standard deviation is the number of trials times the probability of success times 1 minus the probability of success. So let's do that. The number of trials possible, and I'm going to just erase this. The number of trials possible is 500 times the probability of success, which is 0.546 times 1 minus 0.546. What is that? It's 123.942. Let's just make sure I did the formula right. It's N 500 times probability of success times 1 minus probability of success. Now all I got to do is take the square root of that. I got N, which is my 500. 0.546 is probability of spam. 1 minus 0.546 is the probability not spam. Square root of that. And I got 11.13. So our standard deviation, one standard deviation away, this is 11.13 away from 273. So it's 284.13. This is the other side, so it's 262 and something else. It's approximately that, and it's approximately that. Now we have our values. Now we can find, do we have 68% in the middle? So, how would we do that? We do the binomial dist of this first 284 right there, because we want to, it goes to the left. Excel calculate to the left. So it's 284 times the total number of trials times the probability times cumulative. That gives us the probability to the left from that. But we also have to find this 262. So let's do that. Equals binomial dist 262 trials is 500. Probability is 0.546. Cumulative is 1 again. What we end up getting is equals that minus that to get our middle. And our middle is approximately 0.676%. So what we're getting when we find the probability in the middle using binomial dist is 0.676. This is actually really, really freaking close to 68%. And so now we come to the crux of the matter. Can the empirical rule be applied to the binomial distribution in this case? And the answer is yes, it can. We have proven that there's 68% in the middle, which is exactly what the empirical rule says. If I guarantee you, if we do this out again and we do 261 and we do 285, and I'm just doing approximate numbers because I want to sort of get this right. It's 295, in fact. We're doing 295 equals binomial dist 295, comma 500, comma 0.546, comma cumulative. And then we're doing binomial dist equals binomial dist number of successes, which in this case is 2 standard deviations away from the mean, is 251, not 61. I got that wrong. 251, 500 trials, 0.546, cumulative. You do the top minus the bottom, you get 95%. 2 standard deviations is 95%. So the crux of the matter, can the empirical rule be applied to this? Yes. And I sort of think I've proven to y'all that you can actually do probabilities using binomial dist, that each outcome, 273, our expected value of 273, represents, according to our Excel formulas, that at exactly 273, our expected outcome, it has a 3.58% chance of occurring. But that 3.58% of occurring at 273 also means there are 52% chance that you have 273 emails or less this side of the graph that have spam. And each of these values, 479 has a probability of occurrence, 3 has a probability of occurrence. You can actually use this as sort of an indication of how much data is actually in those ranges. You can actually plot a normal distribution if you want to. You can actually sort of map the empirical rule onto the normal distribution to really sort of be able to analyze, does the empirical rule exist? I hope this helped, and I hope you have a great night. Thank you.